Welcome to today's paper reading. Today's paper is titled, Better and Faster Large Language Models via Multi-Token Prediction. This paper was published on the AR14 preprint by Fabian Gloeckle and colleagues from FAIR at Meta. In this work, the authors propose a novel approach to training large language models by predicting multiple future tokens at once. This method, which uses an independent output heads on top of a shared model trunk, results in higher sample efficiency. The authors found that this multi-token prediction strategy improves downstream capabilities without increasing training time, making it particularly beneficial for larger models. Notably, their 13B parameter models showed significant gains on generative benchmarks, solving 12% more problems on human eval and 17% more on MBPP compared to next token models. Additionally, models trained with 4-token prediction demonstrated up to 3 times faster inference speeds, even with large batch sizes. The current approach of next token prediction in large language models, LLMs, is inefficient as it focuses on local patterns and requires significant amounts of data. In contrast, multi-token prediction, which involves predicting multiple future tokens simultaneously, is proposed to enhance sample efficiency and overall model performance. This study introduces a simple architecture for multi-token prediction without additional training time or memory overhead. Experimental results show that this method is beneficial at scale, improving problem-solving capabilities and enabling faster inference times. The authors hope this work will encourage further research into auxiliary losses beyond next token prediction to further enhance LLM performance. Figure 1 provides an overview of the multi-token prediction process. At the top, during training, the model is designed to predict 4 future tokens simultaneously, utilizing a shared trunk and 4 dedicated output heads. During inference, only the next token output head is employed, although the other 3 heads can optionally be used to accelerate inference time. The bottom part of the figure demonstrates that multi-token prediction significantly enhances performance on the MBPP code task, particularly as the model size increases. Error bars represent 90% confidence intervals calculated through bootstrapping over dataset samples. In standard language modeling, the task is to predict the next token using a cross-entropy loss function, denoted as L1. This involves maximizing the probability of the next token given the history of past tokens. In this work, we extend this approach to a multi-token prediction task, where the model predicts n future tokens simultaneously. This is achieved by modifying the cross-entropy loss to Ln, which considers the probability of a sequence of future tokens. To manage the computational complexity, we use a shared transformer trunk to generate a latent representation, which is then fed into multiple independent heads for parallel prediction. This architecture significantly reduces GPU memory usage, from O and D plus D to O V plus D, without affecting runtime. Figure 2 illustrates the order of the forward and backward passes in an n-token prediction model with n equals 2 heads. The key innovation here is the sequential computation of the forward and backward passes for each independent output head, which allows the model to avoid materializing all unembedding layer gradients in memory at the same time. This approach significantly reduces the peak GPU memory usage, making the model more memory efficient without compromising runtime performance. In this section, we explore the impact of multi-token prediction losses through extensive experiments. Firstly, we examine how the benefits scale with model size. We train models ranging from 300 million to 13 billion parameters on a large corpus of code. The results indicate that multi-token prediction models become increasingly effective as the model size grows, outperforming single-token prediction models at larger scales. Secondly, we investigate the inference speed improvements. By implementing speculative decoding, we achieved a significant speedup of 3 times for our 4-token prediction model. This method also allowed for an average of 2.5 accepted tokens out of 3 suggestions, demonstrating its efficiency. Lastly, we look at how multi-token prediction promotes learning longer-term patterns. In the extreme case of byte-level tokenization, our 8-byte prediction model showed remarkable improvements, solving 67% more problems on the MBPP benchmark and 20% more on human eval. These findings highlight the potential of multi-token prediction in enhancing both performance and efficiency in large language models. Figure 3 presents the results of N-token prediction models evaluated on the MBPP and HumanEval benchmarks across various model sizes ranging from 300 million to 13 billion parameters. The evaluation metrics include pass at 1, pass at 10, and pass at 100, with 1,000 samples used for each. The figure shows that while multi-token prediction models perform worse than the baseline for smaller models, they significantly outperform the baseline as the model size increases. Error bars indicate 90% confidence intervals calculated using bootstrapping over dataset samples. Table 1 presents a comparison of models with 7B parameters trained from scratch on 200B and 314B bytes of code across the MBPP, HumanEval, and APPS benchmarks. The data indicates that multi-token prediction significantly outperforms next-token prediction in these settings. All performance numbers were calculated using the estimator from Chen et al., 2021, based on 200 samples per problem. Optimal temperatures for each model, dataset, and pass at K were chosen based on test scores, ensuring these are oracle temperatures, as reported in Table S12. Figure 4 illustrates the comparison of fine-tuning performance on the code contest dataset. The study involves fine-tuning a 4-token prediction model using either 4-token or 1-token prediction as the training loss, and comparing these results to a baseline next-token prediction model. For evaluation, 1,000 samples are generated per test problem at various temperatures, and pass at K metrics are computed. The figure highlights that both methods of fine-tuning the 4-token prediction model yield better results than the next-token prediction baseline. Notably, fine-tuning the 4-token prediction model with next-token prediction appears to be the most effective approach overall. This evaluation uses a temperature oracle to maximize pass at K, indicating the model's capabilities in understanding and solving tasks, as well as generating diverse answers. Figure 5 illustrates the performance of 7B models trained on 200B tokens of language data using multi-token prediction. The figure shows the average accuracy evolution across 6 standard NLP benchmarks. Notably, the 2 future token model performs on par with the next token prediction baseline, while the 4 future token model experiences a slight performance degradation. These results suggest that larger model sizes may be required to observe improvements in choice tasks. Figure 6 illustrates the performance of 7B models on abstractive text summarization tasks, showing the average Rozière F1 score across 8 benchmarks. The models were trained on 200B and 500B tokens of natural language data. After fine-tuning for 3 epochs, the checkpoints with the highest Rozière F1 validation scores were selected. Notably, both N=2 and N=4 multi-token prediction models demonstrated superior performance compared to next-token prediction models. Detailed scores for each dataset are available in Appendix H. Figure 7 illustrates the induction capability of N-token prediction models, focusing on the accuracy of predicting the second token of names that have been previously mentioned. The figure compares models trained with next-token and 2-token prediction losses, showing 2 independent runs for each. Notably, next-token prediction models exhibit significantly lower induction capability for small sizes, but this disadvantage diminishes as the model size reaches 100 m non-embedding parameters. Figure 8 illustrates the accuracy of models on a polynomial arithmetic task, varying the number of operations per expression. The data shows that training with multi-token prediction losses enhances accuracy across different task difficulties. Notably, this approach significantly boosts out-of-domain generalization performance, even though the absolute level remains low. In contrast, simply tripling the model size has a much less pronounced effect compared to switching from next-token prediction to multi-token prediction loss, as highlighted in Figure S16. The results are based on 2 independent runs for each configuration using models with 100 m parameters. In the related work section, we discuss various approaches to language modeling losses. Dong et al., 2019, and Tay et al., 2022, use a mixture of denoising tasks with different attention masks to improve performance on generative tasks. Tay et al., 2022, also employs a span corruption objective, which replaces spans of tokens with special tokens. Additionally, Yang et al. 2019 train on permuted sequences, which allows predicting beyond the next token. Moving on to multi-token prediction, Chi et al. 2020 argue that this approach encourages planning and improves model representations by preventing overfitting on local patterns. Finally, regarding self-speculative decoding, Stern et al. 2018 propose a scheme for faster inference, which our architecture adapts by replacing linear prediction heads with transformer layers. Figure 9 illustrates how multi-token prediction loss assigns higher implicit weights to consequential tokens. The sequence shown has all transitions except 5 as easy to predict. The difficult transition 5 is hard to predict in advance, thus receiving a higher implicit weight in the overall loss. This is influenced by its correlates 3A 5C, which are also hard to predict. In this study, the authors propose multi-token prediction as an enhancement over traditional next-token prediction in training language models for generative or reasoning tasks. Their experiments, conducted on models up to 7 billion parameters and 1 trillion tokens, demonstrate that this approach becomes increasingly beneficial for larger models, particularly showing significant improvements in code-related tasks. The authors suggest that their method helps reduce the distribution mismatch between teacher-forced training and autoregressive generation. When combined with speculative decoding, exact inference speeds up by a factor of 3. Looking ahead, the authors plan to investigate methods for automatically selecting the number of tokens, n, in multi-token prediction losses, potentially using loss scales and balancing techniques. They also anticipate that optimal vocabulary sizes for multi-token prediction may differ from those for next-token prediction, and tuning these could yield better results and improve trade-offs between sequence length compression and computational efficiency. Finally, they aim to develop auxiliary prediction losses that operate within embedding spaces to further enhance model performance. Thank you for watching.